Thank you, Jose. It's a pleasure to be here. I've actually got my family here at a beach house at Mission Bay, so it's a very special week. So in writing this talk, I gave Jose this title, The New Job for Telescopes. And then as I think about it, as this is an optical audience, I wanted to go a little bit broader. So I spent the last 5 years trying to think what of everything I've learned in my career could be useful in the general problem of doing something about climate change. I think, the question for our generation will be, what did you do, Daddy, about climate change? Because I think as time goes on, it'll look like the biggest problem of our time. So I wanted to start a little bit then broadly about what optics can do in this direction, at least a couple of the things that I've thought about, and then I'll focus more on the solar electricity part. So I'll say a little bit then about how you can cool the planet with optics, if you like, and what optics has to do for that. And you can cool the planet if you block 2% of the sun's light that would otherwise get to the Earth, then you restore the temperature to pre-industrial amount. The question is, how most efficiently can you do this? You would think something to block sunlight wouldn't require much in the way of optical skills, but it actually helps to know optics if you're going to make that. And then that proves to be very expensive, so the other thing I'll talk about is what we can do with optics to reduce the cost of solar electricity. And the bad news about solar electricity is that it's about 3 times too expensive to be at cost parity with fossil fuel, and the good news is there's only a factor of 3 to go. So it's a possible reach to get the price down so that it will be used universally. Obviously, in the realm of optics, there's many, many things to do with energy efficiency, and I can't touch on everything in this talk, and I haven't thought much about that, except that I did figure out that my round trip here to San Diego cost about 400 kilograms of carbon dioxide in the atmosphere, and if we had better optical communications and fibers and convenient ways to interact without getting together, that would save a bit. So the climate change problem, and I'm sorry I'll go very quickly through the sort of Al Gore reduction here. So this is the record for the last 400,000 years. These are the facts. So from Antarctic and Arctic ice, you find that carbon dioxide and temperature of the planet are very, very tightly together. They follow about as perfectly as you could imagine through the glacial and interglacial periods. And then this is focusing in the purple on the last 400,000 years of carbon dioxide. And on the right-hand end is where we're going. So at the time I made this slide up, we were at around 380 parts per million. So the glacial to interglacial is about 100 parts per million from about 180 to 280, and we're now at 380. So you don't have to use huge computer models to at least have a guess at what could happen. So one thing we see is that the heating has started. One thing we know is that the time constant is pretty long, both for the planet to respond and for carbon dioxide to go away. So they're both in the hundreds of years. So we ain't seen nothing yet. This is just the beginning of the response of a system with long time constants. So this plot shows the bottom 2 dots show the measured variation in sea level and the measured temperature change. So this is through the glacial and interglacial periods. So the change in sea level is about 130 meters for a change in temperature of about 6 degrees C. And if you look at what you think that increase of CO2 could do, it could very easily take you through the few degrees more to melt everything. And everything would be a 60-meter rise. So I'm staying at this wonderful beach house at Mission Bay. So I was just thinking, well, it's bye-bye to all of that without much sea level rise. And of course, to hundreds of millions of people in their homes and species and ecosystems. There's just a huge amount at stake. And you have to be very brave to think that those simple measurements actually don't point you to worry very hard about what's going to happen. So the first thing I thought about was, this is an old idea, is that you can put spacecraft at the L1 point, which is about 1% of the distance towards the sun. And if you put enough stuff there, it will block out sunlight that would otherwise have got to the Earth. You have to think a little bit, because the Earth doesn't stay in a nice circle that wobbles because of the moon, but those numbers work out all right. So we need to put something up at L1 that has roughly 2% the area of the Earth, which is about 1 million square miles. And people have talked about putting moon dust or whatever up there because it's easier to launch. But if you launch something from the Earth, you can afford to fabricate something that is very efficient in how it blocks light. And one of the constraints you have to worry about, you might think, well, you put mirrors up there, thin mirrors, but radiation pressure completely upsets the orbit at L1 if you put very lightweight mirrors. So it's better to put a refractive sort of diffraction grating material that actually doesn't block the light, but just deviates it a little bit. And so what I came up with that is that the lightest possible thing that you could put at L1 is actually a screen with holes in it. The screen needs to have an optical thickness of half a wave so that what goes through the holes and what goes through the screen cancels out by interference. And of course, the energy has to go somewhere. If you put the holes at the right spacing, then the diffracted light can go a degree or so, and so the light that would have hit the Earth from the sun is deviated away. So that gets you down to about 6 million tons of ceramic or something that will stand a lot of UV radiation, and you'd probably need to launch about 20 million tons of stuff to do that. So what I looked at there, unfortunately, the L1 orbit is not stable. It's metastable, and so anything you put there will gradually drift off. So you could imagine you could put a lot of moon dust up there, but it wouldn't last very long, maybe a couple of years before it wanders away. So unfortunately, you have to put these screens in the form of little spacecraft that have just enough brains to hold them on course. And the spacecraft I came up with were 2 feet in diameter, and there's a few trillion of them, and they have a very small brain on each one. A hummingbird can fly a long way with this little brain, and it doesn't weigh more than a gram. So it seems reasonable you could put enough measurement to keep these things on course using radiation pressure to steer them. So looking through these things, the stars or the sun turn into some diffraction spots which average out into a circle. So you could think that could be stable for 50 years. The bad news is that it would probably cost, in my estimate, including the launch costs, would be several $1 trillion, which actually for 50 years works out to 100 billion years, which is nothing to cool the planet. However, the political task of getting the planet organizations and politics together to do this, I think, would probably be impossible. So there is a technical solution. I think a lot of people imagine that somehow scientists will come up with something that's going to fix this problem. But as you go through, we do a certain amount of magic, but it has to form within the realm of physics and optics. And so the general public may think that something will come along, but it's up to us to think out what's actually possible within the laws of physics to fix this problem. So this is one of the things that doesn't violate physics. Even the economy of it's not bad, but the politics of it are probably messed up because it requires a collaborative effort. So a better way, I wrote a big paper on this, and then I walked away from it because it was out of my scope at that point. Politics is not what I do. So let's think of the other more obvious thing, which is, so CO2, this is CO2 emitted by the US. And you can see in the dark blue, dark and light together is all CO2 sources. And something like half of CO2 is used in generating electricity. So if we can figure out how to make electricity from sunlight, and you don't have to get the whole world to cooperate, you just have to get the price at a level or a bit less than fossil fuel, and there will be an automatic transition to whatever the cheapest fuel is. So this seemed to be a much more likely project to deal with climate change with optics. So you want to replace basically fossil fuel generated, and I'm afraid that includes natural gas. At least we have maybe a little bit of grace, but it's still, in the burning of natural gas, is half of the carbon of coal. And in getting the gas out of the ground, there's a significant CO2, which I haven't quite figured out how much that is. Some people say it's as much as coal to get it out, but I can't give an answer on that. So it is possible to imagine putting together wind and solar and hydro and some storage and making a complete renewable system for the US. And the picture I was drawing a few years ago is something like this. So the picture of the US with where the electricity is consumed in terms of the city lights. And then you basically have more renewable resources, except for hydro, which is pretty uniform. Wind tends to be in the Rockies and solar tends to be in the Southwest. But you can imagine that it would be possible to put transmission lines, and if you do Ohm's law, you find that you can send electricity from Arizona to New York with only a 10% loss with a million-volt transmission line. And in fact, the one little arrow at the left, which is heading down towards Los Angeles, is a half megavolt DC line that brings hydro from Washington State to LA. And that's been in operation making money for at least a couple of decades. So there is, if you want to do it, you can build transmission lines to take renewable energy over large distances. And if you go from half to 1 megavolt, that's a doable thing. So you can store energy with pumped water, and there's already a lot of that for nuclear storage, so it's an established technology, and put together hydro, wind, and solar and do the whole nation. So if you look ahead at what's needed, we presently have about 1,000 gigawatts of electricity in the US, and over the next 40 years, you'll probably have to build about 2,000 gigawatts of new plant because the lifetime of utilities is about 40 years. So that means you need something like 40 gigawatts. One way or another is going to get built of something, and some significant fraction of that could be solar. And so the financial drive, if you can get the price, the DOE, and there's a general agreement that you need to install facilities at about $1 a watt. So you'd have some fraction of a $50 billion a year industry. So you young people who previously went to Wall Street if you wanted to get rich, now you want to go into solar energy and cash in on some of this. So the idea of making solar steam, at any rate, has been around for a long time. This is about 1880. And in fact, remarkably, most utility scale generation, I think it's still most, it certainly was until recently, is by steam generation with solar. And although PV is coming along and will probably take over in daytime for sure, making heat and making steam or some kind of turbine, we can expect to last for a good while because you can store heat overnight. So you can do something that PV will never do. And there's some of that been implemented, mostly in Europe, and still at the stage where government subsidies, like everything in solar, but I think particularly in solar thermal storage, you need subsidies to make that go. So let's get into some optics. This is the now 20 years or more old SEGS plant in the Mojave Desert. So here we have mirrors that are cylindrically curved and focused to a line. And along that line is a steam pipe inside a vacuum coated with coatings to suppress radiative loss, but to absorb the optical light. And these things are built. There was a big gap, but in the last 5 or 10 years, a lot of these have been built, particularly in Europe. And this is the kind of construction that people use for these steam pipes. So the brown things there are sheets of 4 millimeter thick glass, which is curved into a cylindrical shape and then silvered and painted on the back. And then this cylindrical trough, which is about 5 or 6 meters wide, is made up of about 4 of these going across. And then a typical unit is 100 or 200 meters long. So that's sort of the state of the art, if you like, in steam pipe generation. Here's a unique one. Mostly these things have run oil through the pipes, which can run to about 400 C. So the thermodynamic efficiency is not so great. You're not as hot as in regular utility steam plants. This is a unique one in Italy where this hot liquid salt is run down the pipes, and that runs at close to 600 C. So that gets up the thermodynamic efficiency a bit. These things are absolutely heroic in the engineering because you have to have these pipes. They've got to be in a vacuum. They have to rotate. You have to allow for the drives failing and one not driving with another. So there's a mass of technology, but they're quite old. Here are some trough plants with oil in Spain, but they are with tanks to store the hot oil so that they give 7-hour storage into the night. The hexagon was a plan that I was dreaming of, but underneath is a real plant in Spain. So the issues with these things, they're not so wonderful in winter because the economical tracking is to turn the mirrors about a north-south axis, and so in winter when the sun is low in the sky, you lose efficiency. There's a limit to how hot the temperature is, and in order to get even up to the 600 C, you need very accurate optics. I think I've touched the other things. It does need water, which is scarce in the desert. So you can do concentration in 2D, and this is currently the most popular thing. So there has been quite a lot of work done with parabolic dishes, with small Stirling engines at the focus, but those turn out to be probably the most expensive of the thermal things. This is a way to bring light to a point focus, but with a field of heliostats. And so each of these is individually controlled to reflect light to a tower. And now you can get concentrations of 1,000 times at the tower, and you can make much higher temperature, although at the moment, power tower systems are limited to using steam at about 600 C, which is the sort of, in power plants, that's the limit for the Rankine cycle. If you want to use Brayton cycle, you need around 1,200 C, and that hasn't yet been implemented in power towers. So there's still not so, they can use commercial turbines, but the optics, if you want to bring light to a point focus, you really want a paraboloid. You don't want a bunch of things spread out on the ground. So you lose efficiency because of the geometry here. So it's poor efficiency. You need pretty large land area to work these things. The overall conversion efficiency, that's the sunlight landing on the mirror to the electricity coming out, is about 18%, and the cost is still pretty high. So this is one example. Here's a field. This is some work by MIT. If you look at all the mirrors in the field, which have the same geometry as a sunflower, then because of the way the angles go over the year, it's really only the mirrors towards the center of the field that are used efficiently. And by the time you get to the outer yellow ones here, only 60% of their area is sort of directing useful sunlight at the tower. But if you, I gave you the long-term vision of the whole nation covered with an integrated renewable system. A shorter-term thing you can imagine is that in the Southwest, you can have one power plant which combines a thermal system for nighttime generation and PV for daytime generation. So without having to invoke new transmission lines or anything, you can take a plant in the Southwest and replace it with a 24/7 plant, which is using a combination of thermal and PV. So we're not so far away from being able to do that if we can get the cost down. So let's think about what we can do for improving photovoltaics in terms of the cost, get them down to this installed cost of $1 a watt. So there's been this huge development and cost reduction for flat panels, I think driven fundamentally by rooftops. So I think about 80% of flat panels, and it's something like 50 gigawatts a year is, I think, the production this year, and maybe 10 gigawatts of that is going into utility power stations. And the simplest thing to do with these is simply plunk them down on the ground in huge fields. And the cost has come down. It's still not an installed cost. We're still a factor of 2 or more away from the cost parity. And the technology is getting fairly mature now, although maybe there's still another factor of 2. But it's not so much in the panel price now, it's in the rest of the system to get it installed. So the efficiency of the best panels is 20%. The thin film panels maybe around 12%. If you keep it cheap and just fix them on the ground, then you get a surge of power around noon, and then because you're not tracking the sun, it falls off in the morning and the evening. So there's still we're not there on price. It needs a lot of land, and unless you go to tracking, these things may generate a lot of watts at noon, but it doesn't last so well in terms of getting energy through the year. So what do we do to improve the simple fixed roof panel? Well, you can turn the panels so that they follow the sun. So you can have a 1D tracker, and the typical one is like the Trough tracker we were seeing. So you have a horizontal north-south axis, and you turn to the east and the west. So you still lose out a bit in winter when the sun is low. You can go to photovoltaic cells with higher efficiency. And it's the property of photovoltaic conversion that if you concentrate the light on the cells, you actually improve the conversion efficiency. There's one slight snag with concentration, which you have to bear in mind when you're working costs, and that is if you've got a flat panel, it actually gets about 20% of its output comes from the diffuse emission from the sky. If you start to concentrate, then you lose that component. So there's no convergence in the utility industry about whether you should use flat panels without concentration fixed, or one axis or two axis, and whether you should concentrate at 1 times or 1,000 times. And I want to say a little bit why there's such a variety at the moment, and see where we can see to getting the best out of what we could do. So from optomechanical considerations, there are really sort of 3 concentrations I think you want to think about or you'd like to get to. One is the fixed, do nothing, no concentration. The other is turning on a single axis and getting about 30 times concentration. And the other is turning on 2 axes and getting about 1,000 times. The reason for those numbers is that when you build any kind of solar thing on the ground, it has to withstand high wind, maybe up to 90 miles an hour. And that means you can't make something too flimsy. And so if you make a static system or one axis, if you can steer it to plus or minus a degree, which corresponds to about 30 times concentration in 1D, and it doesn't really cost you any more than just making it stiff enough to withstand wind. And similarly, if you go to 2D and you have it stable to a degree in either of two dimensions, then you get to about 1,000 times concentration. So those are the natural sweet spots that come from optomechanics. And right now, we have cells that allow you to work efficiently at 1x, no concentration, no tracking, and also with 2-axis. We don't have cells that could get the most out of 1D tracking. So the cells that we can use for 2D at 1,000x come from the heritage of space PV cells. You probably know, and I think there was a talk yesterday from Solar Junction. So in silicon, no matter what the energy of the photon was, it will release an electron with a lot of energy, but what you get out is set by the band gap of the semiconductor. And so if you just have one material, you can only choose one band gap. You have to choose it narrow enough to capture light, in the case of silicon, up to 1 micron. But then that means the energy of the electron that you get from any photon is set by that band gap of corresponding to a micron around an EV. So it's better if you can get the electrical energy more corresponding to h nu of the photon. And you can do that by putting semiconductors in layers, so you have several band gaps. And then the blue photons get caught in the top layer, which is transparent to redder photons, so you can get high energy photons and electrons from the top layer and then go down through different layers. So that lets you approximately double the electrical output for a given amount of sunlight. And that's what's done in all space PV panels. And here money is absolutely no object at all, because the cost of launch is tens of thousands of dollars per kilogram. So it doesn't matter whether the cells were free or very expensive. It's dominated by launch cost. However, what the space PV industry has done, it matters very much about reliability. So over 20 years, these triple junction cells have been developed for space to be extremely reliable. And they're an obvious candidate to work at 1,000x, because if you're going to that concentration, the fact that it's expensive doesn't matter very much. So here's a Boeing cell that we've been using in our experiments. It's around 40%. The world winner, Solar Junction, is 43.5. And we can expect, based on previous experience, that we're going to gain 1% a year for a good number of years, maybe to 50, 55, possibly even 60%. So here's some triple junction cells that we use at 1,000x. And right now, we're making 2.5 kilowatts from 36 of those cells. So it's quite remarkable. You take a very small amount of very efficient semiconductor and make a lot of power from it. So the economics of these cells are different types. So crystalline silicon, which is in the range 15 to 20%, the best from sun power, is of order $200 a square meter. The triple junction cells for space, with twice the efficiency, are about $50,000 per square meter. But that's pretty economical under the 1,000x sweet spot. If you work through those numbers, so for silicon, when the sun's bright, because of the diffuse component, you have about 1,200 watts per square meter, and that works out. The cell cost for the silicon cells is about $1.10 per watt. Triple junction cells, if you run them at 1,000x and 1,000 watts per square meter incoming direct illumination, then the cost is about 12.5 cents per watt. So this is the prize that is ahead of us, those who are thinking about these concentrated cells, is that if you can figure out the optics and the mechanics to get 1,000x concentration without blowing your budget, then the cell cost and the efficiency are very enticing. So in case some of you here are maybe in the cell business, I just wanted to make sure that that middle spot, the one axis 30x, doesn't get forgotten. because if you're making a single axis tracker and it doesn't cost you much more to get to 30x, if you could get cells for less than $2,000 per square meter that gave you maybe 30 and 40% in a few years conversion efficiency, that would be a very interesting domain to go in, because it costs you to concentrate and it costs you to track in 2D. So you have to work out all the numbers very carefully, but there was no space development looking at cells that would be somewhat less efficient and 10 times cheaper. But if somebody could come up with that, that could be a very interesting domain. But right now, the other domains are interesting too, the 1x and the 1000x. And I'll finish up talking a little bit about what we've been doing at the University of Arizona, trying to figure out the optimum optomechanical system to get you to 1000x. And what we realized was that there's a pretty good supply chain which has brought down the price of mirrors and trackers for the solar thermal systems. So I showed you some of those. So there's a factory in Arizona, there are other ones in the nation, but there's one in Arizona that makes the panels for the Trough system, and they're 2.5 square meters. They come off the factory 24/7 at 20 seconds per panel, and they cost about 90 bucks each. And there's another factory in Arizona that's making the trackers there, the Bright Source trackers. These carry 15 square meters of glass, and they're making 170,000 of these trackers. So there's a very high volume from the thermal side in making mirror-type concentrators, and we can sort of write down what the cost is today and how it's likely to evolve, because there are very big factories already doing it. So one of the tricks, though, is that this self-supporting glass, which is the cheapest to support and track, is only available either flat or cylindrically curved. So at the Mirror Lab at the University of Arizona, we figured out a process to shape these big 2.5 square meter sheets of glass to come to a point focus. So these are part of a paraboloid. And we have now a process that works very well, enough for us to make our demonstration systems. And we just got funded by the DOE to take that process and speed it up. So we're hoping to get this, it's a very simple slumping process, but we're building a giant 0.5 megawatt toaster, which we hope will heat the glass very quickly and allow us to shape it very quickly. So we're very pleased that that's funded, and hopefully over the next couple of years we will have a process that can go at the same speed as the 200 seconds per dish, but now with point focused dishes instead of cylindrically focused dishes. So that's one of the bits of evolution from present supply chain that you need to do. The other thing you've got to worry about is that a dish like this will allow you to get, in our case, we've been bringing 10 kilowatts of solar energy to a focus. That's a lot of energy. It's like a serious blowtorch. So if you put a piece of steel at the focus, and we did this for Gabby Giffords, who was very helpful in getting funding to get us started, then in 15 seconds in 1/4-inch steel, you've melted a hole and liquid steel comes down and so on. So this is, instead of optical interferometry to test your mirror, which is what the early part of my career was using, and with Jose involved in that, the test of manhood in a solar mirror is, can you make a hole like this? Because this is, you have to image something like that, an image the size of the sun, and then you can make such a hole. So it tells you that you've made the mirror to the limit of quality that you need for a solar mirror. However, having done that, so why do we bother to do that? Because if we put cells at that point, we would melt them in a heartbeat too. And the reason is that if you control your optics, then one of the things you want to do to bring down the price of the whole optomechanical system is give it tolerance to motion. So we have to make a certain stiffness to withstand hurricanes, but it's nice if you don't have to point to a small fraction of the diameter of the sun in order to keep your flux on the cells. So we devised this optical scheme so the light that comes to the focus that would melt steel, you actually put it in the center of a fused silica ball, and we're using Heraeus fused silica. Sorry, I spelt it wrong, Heraeus, forgive me there. And the point of the ball is it's very pure material. It doesn't melt on the inside. It doesn't even get warm. But what it does do is it forms an image of the dish at the front of this array of funnels that I've got there. And that image is, if you think about it, an image is fixed, so even if you mispoint a bit, so the light is not going to the center of the ball, it still is formed over the same square region of the entrance to these funnels. And you can see in the bottom two pictures that the front entrance of the funnels, they're touching at knife edges, so we cover the entire area of the image. And at the back, the light is funneled out to a set of 36 uniform 15 millimeter squares, and that's where the cells go. So we can make a system that we've controlled this torch of energy coming in, and now got it so it comes out onto the 36 cells uniformly, even when we mispoint the mechanical system a bit. So we've, at the university and with the new company Renew, we've just in the last 2 or 3 months put up our second generation system. So there's a dish which is 3.3 meters on a side. It's focusing light where you see a bit of a glow there. It's focusing on a fused silica ball and then back to the 36 cells behind. Now something that you have to worry about when you use a big dish and put cells together in a small cluster, there's a lot of heat there, because even if you turn 40% of the light into electricity, 60% gets turned into heat, and that's still enough to do a lot of damage. And you can't use passive heat sinks at this point. You can't distribute the heat out far enough with a passive system. You have to have an active system. And so the two black things up there are radiators, and they work just like an automobile radiator. So we're circulating antifreeze to the back of the cells and then out into the radiator. And this is not usually done with these concentrating cells. People are, in general, so concerned not to use active cooling that they go to passive systems, which involve very big cell assemblies and lots of conductive material like aluminum. So we've gone in a different direction to say, let's keep the cells compact and let's go for an efficient radiator. And we're at the stage now where the pump and the fan in the radiator take 2% of the photovoltaically generated electricity. So we have a 2% parasitic loss. We can see how to get that down to 1%, I think. And one of the advantages that you get is active cooling is really good cooling. So I'll show in a minute, our cells run at just 20 C above ambient air temperature. So what we get for that 2% of parasitic power is very good control of cell temperature. And of course, power drops with temperature even with triple junction cells. So you soon get back the whatever parasitic power it was. So here are some results just from the couple of months, the last couple of months. Tom Stolkop, who I'll leave at the end, is talking about this in much more detail tomorrow afternoon. But you see some of the features. We haven't quite got to the theoretical limit, but we have about a degree of acceptance angle with only a 5 or 10% loss of energy. But that's the effect of using the ball rather than just putting the light directly up to the cells. The IV curve, it should be horizontal on the top insofar as you haven't exactly matched the flux going into the cells. It has a slope on it. So we're getting better at that, and as time goes on and we match the exact amount of light coming out of each funnel, we should get that flatter. And we're up to a system efficiency now of about 28%, which is getting into the land of the living. The most that people are getting out of these concentrator systems without any of the parasitic loss or whatever is about 33%. We think in the next generation we should get to that. So there's some more data there. I think that Tom will talk about the 20C temperature difference. And the mirror that we've made has, for those of you in the business, it's got 1.25 milliradians of RMS slope error on the mirror, and that's probably as good or better than any curved mirror by other technologies. So a nice thing here is that when you concentrate in PV, you can either sort of put things together into a big module which looks somewhat like a regular panel you're used to. We prefer to make this separation where the concentration goes to existing supply chain and is separate, and then the cells are confined to a very small assembly. One of the great advantages we're realizing of that is that these cells get better over time. And so in 20 years, you could imagine that if today we bought 40% cells, they're going to be at least 50% in 20 years. And because the cell assembly is so small, it becomes economical to take out the old one and put in a new one. So even if the old one hadn't deteriorated at all, you would probably, after some number of years, find it economical to switch to increased efficiency. So that's a property of multi-junction cells. Not only are they efficient, but they get more efficient over time. So in the past, I built mirrors for astronomy through the university, and you can have, as we do, a $10 or $20 million a year of business selling astronomical mirrors right on the UA campus. If you want to save the planet and make optics in that quantity, it can't be done in the university. So a couple of years ago, I founded this company, Renew, and I was even thought to be a businessman by the local business magazine. So Renew has got the license for the technology, which is in a number of patents held by the university. Tom Storkup's the chief engineer, and he'll be talking tomorrow, and he was responsible for a lot of the beautiful results I just showed. So both Tom and my student Blake Kugano will be talking tomorrow afternoon in 8468. So I think I've come to an end there, so I'm happy to take questions.